All right, we're going to go over chapter 5 now, and chapter 5 is going to be over solutions and reactions that involves aqueous solutions. So anything that's aqueous means it's dissolved in water, okay? So let's talk about solutions here. So what is the definition of a solution? All homogeneous mixtures are actually called solutions, but the solutions that we are going to be concentrating on is basically a solid that's going to go into a liquid to make a solution. The solid that goes into the liquid that changes its phase is going to be called the solute. And then the liquid, because it doesn't change its phase, it's called the solvent. Okay, now if you do have a case where you have a solution where both of them are maybe both liquid solutions, where you have like a mixture of alcohol and water and they're both liquid, the smaller component will be called the solute and the bigger component will be called the solvent. But in our case, we are going to be mainly focused on where kind of like a sugar solution or a salt solution, when you put the solid pieces into water, and when they're solid pieces are called the solute, and the water component, because it doesn't change phase, will be called the solvent. Okay? All right, so to measure concentration of solution, we are going to be using a unit called molarity. Molarity is where you have moles of the solute on the top divided by the total volume of the entire solution in liters. Okay, so that means the bottom here is the solution is made out of solute and solvent. So it means everybody is going on the bottom, the entire solution. On the top, only the moles of the solute. Okay, so the lower concentration or dilute solutions will have a smaller molarity. Concentrated solutions will have a bigger molarity. All right, so let's go ahead and try some problems based on this. We'll do a couple, and then we'll talk about dilutions after this. Okay, first question. 25.5 grams of KBr is dissolved in enough water to make 1.75 liter of solution. Because that's the total volume of the solution here, okay? And it says, what is the molarity? KBr solution, okay? And then you look up the molar mass of KBr from a periodic table, just add K and Br values together, and you'll get that it weighs 119.00 grams per mole. Okay, so if you know that, how are we going to get a molarity? So molarity, the symbol for molarity is capital M, okay? And the symbol for moles, remember, is MOL. So we want to take mole of KBr divided by liter of the entire solution. Okay, so just keep in mind, this here is molarity, this here is moles. So abbreviation, M means molarity, mole means moles. Just want to keep that in mind. A lot of people use M for mole. That's actually wrong, because M stands for meter, M can stand for milli, but it's not mole. And some people use the lowercase m for molarity, and that's wrong too, because it actually means a different unit. Okay, so just make sure you know your unit abbreviations. Let's go ahead and get that going. We need to find moles of KBr. So 25.5 grams of KBr has to be converted to moles. So 1 mole of KBr weighs 119 grams. So we can get the moles of KBr as 0.21429. I'm just going to underline the third number because we only keep 3 suffixes here, but I don't round onto the end. So my molarity here equals to 0.21429 moles of KBr divided by 1.75 liter of the solution. because 1.75 was given in the question here. Okay? All right, so that will give me my answer. If you want to keep 3 sig figs, 0.122 molarity. Okay, so start getting used to these units here, the abbreviations. Don't be using the wrong ones. Okay, so let's go to the next question. The next question says, how many liters of 0.125 molarity NaOH solution contains 0.255 moles of NaOH? Okay, so now they're asking you for volume when they give you the molarity and the moles. So when you're given the molarity like this, always remember this means every time I have 0.125 moles of NaOH, I can find this in exactly 1 liter of solution, of NaOH solution. Okay, that's what molarity means. You just write this conversion down here. And then it says you need to find something that has 0.255 moles. So if I have 0.255 moles that I want to get, and I know that every time I have 1 liter, I will have 0.125 moles based on this right here. Okay, so then we can find the liters in our answer, so the moles cancel off. So in this case, you are going to get the answer as 2.04 liters of NaOH solution. Okay, so it's pretty simple. We just make sure we remember the units is moles of the solute over liters of solution. Now, let's talk about something called dilution. Okay, so dilution of a solution is trying to make our solutions less concentrated. So like, for example, if you buy concentrated acid, like stock solution of acids, they come really, really highly concentrated and they're dangerous. And we always use lower concentrations for our experiments. So we have to dilute these things. Okay, so dilution means in your problem, you only have 1 chemical. It doesn't change. There's no reaction because you're taking that 1 chemical, you're adding water to it, and you're changing the concentration to a smaller number. Okay, so the formula to use when you're doing dilution is molarity 1 times volume 1 equals the molarity 2 times volume 2. So M2 and V2 is for the new solution, M1, V1 is for the original solution. Okay, the reason why is because the moles doesn't change. So we can take molarity times volume equals to the moles, and the moles stay the same from one to the other because all you're doing is adding water to it and it doesn't change the moles of the items. You're not putting in extra solutes or anything. Okay, so that's why this equation works only for solution dilution. So when you read a question for solution dilution, remember there's only 1 chemical involved and adding water to it. There's no like equation involved, changing chemicals. That one you cannot use M1V1 equals to M2V2. Okay, so let's go ahead and try a problem. Let's see, we have some dilution problem to work on. So remember, dilution equation is M1V1 equals to M2V2, okay? And then it says, to what volume should you dilute 0.200 liters of 15 molarity NaOH? See how concentrated that is? 15 is really concentrated. So NaOH solution to obtain a 3.00 molarity NaOH solution. So you're taking the 15 and you want to cut it down to 3 by adding water. Okay, so this is your original. So this is my M1, this is my V1. Okay, and this is my M2, my new molarity. All we have to look for is V2. So you set out your equation M1, 15.0, okay, molarity times 0.200 liter equals to 3.00 molarity times V2 in liter. We don't know what that is. We're trying to solve for it. So to get V2, you have to take 15.0 times 0.200 divided by 3.00, and you will get the answer of 1.00. And that's how you would do a dilution problem. So remember, when you read a dilution question, there's only one chemical involved, and it's just adding water. There's nothing else involved, and that's the only time you can use M1 V1 equals M2 V2. Okay? Now, next thing I want to talk about is we can actually use molarity in our stoichiometric problems, like percent yield stuff, limiting reagent, all that stuff, that all comes back. Now, we used to do grams to moles, moles to mole ratio, and then back to grams. And well, now you can do volume, you can do molarity, you can do moles, like over here, like, you know, whatever it is that has to do with concentration of solutions. Okay, so we're gonna try some questions that has to do with that. So we'll do a few extra than what you have on your notes. So these will be like kind of whatever you see on your exams usually. So the first one that we want to go ahead and work on, go ahead and fix this page here. All right. What volume in liters of 0.150 molarity of potassium chloride solution will completely react with 0.150 liter of 0.175 molarity lead to nitrate solution. The products are lead to chloride and potassium nitrate. Okay, so this question here, it doesn't give you the formula, the balance equation, but you can write out the balance equation on your own, okay? So we gotta know our names again. So let's go ahead and put down what the formula for potassium chloride. Okay, potassium chloride solution will be K positive, Cl negative. So it's just gonna be KCl. And because it says it's a solution, I'm gonna go ahead and put AQ behind it. Okay, and then the next one, it says lead 2 nitrate solution. So lead 2 nitrate. Now lead is Pb, nitrate. So 2 and nitrate is this. Nitrate is NO3 negative 1 charge. So there's 2 positive. I need 2 of these guys. Okay, that's lead 2 nitrate. So if you guys are still having trouble with naming, make sure you go back and check that you are memorizing your polyatomic ions and you know how to write names or how to associate names with formulas. All right, so it says the next thing is the products are lead 2 chloride, so it's PbCl2. And then it's potassium nitrate, KNO3. Okay? All right. So the reason why I know this is a solid is because we have to talk about what's coming next. It has to do with precipitation, but we'll worry about that in a little bit. Okay, trying to fix my paper because it's not wanting to be straight. Oh, that's what I have to do, I guess. The book will always be crooked like that. That's so frustrating when I put stuff in and try to fix it. It's just stuff. Sorry guys, my book is just crooked. Anyway, let's keep going. All right, we gotta make sure this equation is balanced. So we gotta do our balancing again, okay? So I'm gonna go ahead and start with potassium and that guy right there, okay? So actually, no, I don't want to do potassium. Let's go ahead and do lead first because lead seems more complicated. Yeah, so let's do lead here. So lead and lead, that's okay. And then we can do nitrate after that because we did lead and lead. And then really we can do chlorine too, whatever. But anyway, I'm gonna do nitrate. And then nitrate here, I will make sure I put a 2. There's 2 here, so I gotta put a 2 this side. And then now I got 2 nitrates and 2 potassium, which means I need to have a 2 over here. And then I'll have 2 chloride ions here, which is 2 over here. So now it's balanced. Okay, so basically to balance it, you did have to add some numbers in there. And now we have a balanced equation. Now we can talk about a problem. Okay, it says 0.150 molarity of potassium chloride. So we don't know the volume. We don't know this, but we know this is 0.150 molarity. Okay, and then it says we have exactly 0.150 liter of 0.175 molarity of this guy. And it says how much of this will all of it react with that. So basically use all of this and make sure to calculate exactly the correct amount that you need to react with lead to nitrate. Okay, so you need to know the mole ratio. The mole ratio is 2 KCl to 1 PbNO2, PbNO3 2. Okay, so find the moles from here first. Okay, you'll get these whenever you have molarity and volume, you can get moles. So get the moles of PbNO3 that way, lead to nitrate, and then you use that mole to mole ratio, get the moles of KCl, and then from the moles of KCl, you have the molarity, you can find the volume. Okay, so what I'm going to go and do is go ahead and start saying, well, I know I have 0.150 liters of PbNO3 2. Okay, now what I'm going to do is then use my molarity. I should always just stick to using my ruler. And then my molarity is 0.175 moles of PbNO3 2 per 1 liter. Okay, so now I can cancel out the liters basically. And then after that, I have moles of PbNO3 2. The ratio is 1 mole of PbNO3 2 to 2 moles of KCl. Okay, now once you have that, 2 moles of KCl, we can go ahead and then use the molarity here to convert it back to volume in liters. So the molarity is 0.150 moles KCl, and every time you have that amount of moles, it's found in exactly 1 liter of KCl. Okay, so all this here, we'll be able to give you the answer in liters because the liters of lead nitrate cancel out. Then you cancel out the moles, then you cancel out the moles of KCl. Now you have answers in liters of KCl. In this case, we want to go ahead and keep 3 sig figs because there's 3 here and 3 here. And our answer is going to be 0.350 liter. Okay, the reason why we're not worried about this 2 here, that's 3 also, is because this one here is exactly 2 to 1. So these are unlimited sig figs right here. So we do keep 3 sig figs in our answer. Okay, so that's your answer for this question here. I'm gonna fix this first. I'll fix it one day, just not today. It's hard because the bottom is like stuck. All right, let's do a few more questions. I actually have quite a few because we like to practice this kind of math, okay? The more practice, the better. So what I want you guys to do is redo these problems again later. So the next question is, what volume in milliliters this time of 0.305 molarity silver nitrate is required to react with exactly 155.0 milliliters of 0.274 molarity of sodium sulfate solution. The products are silver sulfate and sodium nitrate. Okay. Okay, so let's go ahead and write the equation. What's our equation? Silver nitrate is Ag and NO3. Both are +1 -1, so it's 1-to-1 ratio, that's that. And then it says it's reacting with sodium sulfate. So what's sodium? Sodium is Na, sulfate is SO4, and it's 2 negative charge of sulfate. So you need 2 sodium to pair with it, okay? And then it says you're going to make silver sulfate, so Ag2SO4 plus sodium nitrate, NaNO3. So you're going to have to get good at starting to name these things. Now let's go ahead and try to balance this, okay? We'll work on silver first because that's what I'm seeing right here. I'll put a 2 here. So I have 2 nitrates. I'll put a 2 here. That's sodium right there, sulfate. So this is now balanced. Okay, and it says here you need the volume. You don't know what the volume is, but you know it's 0.305 molarity. And for this second guy here is 155 milliliters of 0.274 molarity. Okay, so we'll do the same thing here. The only thing now is, these guys are in volume of milliliters, so you will just have to change from milliliters to liters, okay? Let's go ahead and start the same thing. We'll go ahead and get moles of this guy. So 155, 0 milliliters of Na2SO4. And then you know your molarity in this case. This thing is just stuck here. We can fix it. Okay. I'm just going to struggle with it. Yeah, I think I'll just rip it off if I keep messing with it. Okay, so 155 mils, and then you have 274. So 0.274 is moles per liter. So I guess we can go ahead and change it to from milliliters to liter first. What's the conversion? 1 liter of Na2SO4 is in 1,000 milliliters. Okay, so we got that now. That one's good. And then now we can go ahead and use the molarity. And 1 liter, you will get 0.274 moles. And this is still Na2SO4. Okay, once you do the moles of Na2SO4, we do the mole to mole ratio. 1 mole of Na2SO4 is reacting with 2 moles of AgNO3. Okay, now we have AgNO3 there, and then now you just gotta get the volume and you gotta get it in milliliters. So the molarity of that guy is 0.305 moles of AgNO3 per 1 liter. Okay, that's what molarity stands for, moles per liter. And then this is liters of AgNO3. And now let's convert it to milliliters. 1 liter has 1,000 milliliters. Okay, so in the end, you'll get your answer. And we want to go ahead and keep 3 stick picks here, because that's 3. It's a limiting. That's 3 here, and that's 4. But we'll keep 3 in that answer. So you end up getting 278 milliliters of AgNO3. Okay, so that's how we would do that problem. So let's try some more. One more like this. So why don't you guys try, after you see the question, pause it and try to work out the problem on your own. See if you can get the answer to match, okay? So, oh wait, hold on. Did I finish? Yeah, they were asking for a long milliliter, so we're good. Okay, let's go ahead and try one more now, or a couple more. I'm going to go ahead and write out the question, and I write down the multiple choice answers for you so you can try to see how you're going to work this out. Determine the concentration of solution prepared by diluting. So this is diluting, right? So this is a dilution question. Diluting 25.0 mils of a stock 0.188 molarity calcium nitrate, so CaNO3 solution to 150.0 milliliters. Okay, so I'll give you the answer choices here. A is 1.13. 1.13 molarity. B is 0.313 molarity. C is 0.501 molarity. D is 0.0887 molarity. So remember, this is a dilution problem. So you do M1, B1 equals to M2. Okay, so we have our volumes and our molarity. So stock is 25 and 0.188. Okay, so we'll do that. 0.188 molarity, 25. And then M2 is what we're looking for. V2 is 150. Okay, let's solve for M2 here. M2 is 0.188 times 25.0 divided by a 150.0. You will get 0.0313 molarity. We're keeping 3 stick picks in our answer. So the answer here will be B. Okay? All right, let's do another different one. This one says, according to the following reaction, what volume of 0.244 molarity KCl solution is required to react with exactly 50.0 milliliters of 0.210 molarity PbNO3 to solution. So the equation given is 2 KCl plus PbNO3 2 goes to PbCl2 plus 2KN. Okay, so in this case here, we're going to go ahead and write down what we have. you have KCl, you have 0.244 molarity. The other one you got 50 mils, and the molarity is 0.210. So we'll do the same thing here. You get the moles here, 1 to 2 mole ratio from here, and now we can get the volume. So I'll give you the answer choices of your volume. It's 97.4 mils, 86.1 mils, 43.0 mils, and D is 116 mils. So we'll have to work it out, and let's see what you guys get. So take a pause right now, try to work this problem out, see if you can get one of these answers, okay? All right, I'm gonna go ahead and work it out now for you guys as well, assuming you've done it or tried to do it. So we take 50 mils of PbNO3, 2, and then, let's see, let me try to write a little small, maybe I can figure it out. Okay, and then my molarity is in, so this is in 0.210 moles per liter. So I do have to go ahead and change it from milliliters to liters. So 1 liter, NO32 is 1,000 milliliters. And then we'll do the molarity. 1 liter of PbNO32 has 0.210 moles. And then on multimole ratio, 1 mole of PbNO32 is to 2 moles of KCl. Whew, running out of space. And then 2 moles of KCl is right there. So 0.244 moles of KCl is to 1 liter of KCl. Now one more step. After you change the liter, I'm going to go ahead and try to cancel the liter. 1 liter of KCl has 1,000 liters of KCl. And then, so that part comes over here, okay? Let's continue right there. And you should be able to get your answer over here. Put all these on the top, multiply, divide by stuff on the bottom. And include this line here, you get 86.1 milliliters. And that's your answer right there. Okay, so not too bad, not too completely difficult, but you know, I want you guys to go ahead and keep practicing because there's a lot of different kinds of problems that you will be able to see on your homework and quizzes as well. All kinds of extra credit assignments as well. All right, so let's try this next one. The reaction of 25.0 mils of an unknown concentration of sulfuric acid. You're like, okay, what's the formula for sulfuric acid? You gotta remember this. Sulfuric acid is from sulfate because 8 turns to ic. This is an oxy acid, so this is H2SO4, okay? Anyway, this sulfuric acid, and this is the reaction of 25 mils of an unknown concentration of sulfuric acid requires 83.6 milliliters of 0.12 molarity lithium hydroxide solution. The products are lithium sulfate and water. Okay, so lithium sulfate and water, and then it says, what is the concentration of sulfuric acid? What is the molarity of sulfuric acid? So to do this one, we'll have to write the equation out. So we talked about it, H2SO4 as sulfuric acid, lithium hydroxide as LiOH. and you make lithium sulfate, Li, and then SO4, but this is 2 negative, so I need Li2, okay? And water. So this is a type of acid-base reaction, so we'll be talking about this later in the next part of this chapter 5 here. But that's our equation here. Now we gotta make sure it's also balanced, okay? So I have, let's go ahead and do, so here's a little part that's a little more tricky. So you see how there's water and you're like, well, there's no water here. So I have to figure out how I did that, because before this we were talking about ions. But I do want to make sure you remember, water is made out of H plus and OH minus. It's a combination of that. Now I can see I have 2 H plus and then 1 OH minus. So I know my water here is going to come from the OH and the H right there. Okay, so I'm going to be able to see that my lithium here, I need 2 of them. So I'm going to go ahead and put a 2 on this guy. And because of that, I have 2 OH and 2 hydrogen. So now I have water, 2 OH and 2 hydroxide. I'm going to end up making 2 waters. Okay, so that should balance it out now, because sulfate you only have 1. So now that we have that, say this guy here was 25 mils. We don't know the molarity, but we know that this one took 83.6 milliliters and 0.12 molarity. Okay, so now we have that, we have the multimole ratio. So the trick here is really naming and balancing the equation before you can use it for stoichiometry problems. All right, so let's go ahead and try working this out. I'm going to go ahead and write the ABCD choices, and you can go ahead and start working on the math, and then we'll see if you can get the same answers. A is 0.20 molarity. B is 0.10 molarity. C is 0.40 molarity. D is 0.25 molarity. E is 0.36 molarity. Okay, so now that we have that, we can go ahead and start working out the math. And if you haven't already, I'm going to go ahead and work it out so you can see how it's done. We will take the volume, 83.6 milliliters, LiOH. We're going to run out of space again because I just started off high enough. We'll continue on the bottom. And then you have 1 liter is 1,000 milliliters. And then molarity gives you the moles, so 1 liter of LiOH contains 0.12 moles of LiOH. And then we'll go over here, multimole ratio, 2 moles of LiOH is to 1 mole of H2SO4. And then you will have the moles here. Okay, so we are looking for the molarity, so we have the volume here. So we'll stop this right here to get our answer in moles. Because once you have moles and you have the volume, you can get the molarity. So in this case here, we'll stop right here, get the moles, and the moles here, we want to go ahead and keep really just 2 sig figs. So I'll write down a bunch of numbers, 0.005016 moles of H2SO4. But we are limited by just 2 sig figs here. Okay, so I'll go ahead and underline the second number, so it's right there, 50. And then we'll take that moles here to divide by the volume in liters. So 25 milliliters divided by 1,000, you can get liters, and you will get the answer of 0.0250 liters down there. Okay, that's 25 mils in liters. How do I get that? It's just divide by 1,000 because 1,000 mils is 1 liter. And then over here, we will put the moles back in. And then put the moles divided by the volume, you'll get the answer of 0.20 molarity. So that should give us an answer of A. Okay, so Let's go ahead and do one more. Really, I just want you guys to practice naming and balancing equations. So this next one that we want to do, the reaction of 80.0 mils of an unknown concentration of phosphoric acid requires 126 mils of 0.218 molarity potassium hydroxide. Okay, what is it? What is the molarity of phosphoric acid? All right, your answer choices. Well, we have 5. I'll write it out. 0.0461 molarity, 0.138 molarity, 0.343 molarity, 1.03 molarity, 0.114 molarity. So these are all your options here. And I'm sure you guys will be able to do this by now. You have to write an equation. So how do you write the formula for phosphoric acid? Phosphoric acid is H3PO4, okay? And then that's aqueous, and then you have KOH, that's also aqueous. And then potassium hydroxide, that's KOH. And then you have to say, from here, we can make K3PO4. I'll go ahead and help you with that. And then I'll teach you how we can write this equation in the next part. Okay, so that's our equation here. The products are potassium phosphate and water. So they will have told you the product name, but I didn't write it down, so that's my bad. So remember, they'll tell you the products are potassium phosphate and water, and then you can figure it out. And then this is the balanced equation right here, because I have 3, and then I need to have 3 over here, because that only gives me 3 water, and then my phosphate is good, my potassium is 3, so everything's balanced out. Okay, so now that I know the mole-to-mole ratio, a lot of times people don't do the mole-to-mole ratio, they don't balance it, and they get the answer wrong because they forgot it's 3-to-1 ratio. Okay, and then a lot of times the temptation is so high, people use M1V1 and 2V2 here, you also get the wrong answer. So you gotta be careful to know which one that you have to make sure the equations are balanced, and when you can only use M1V1 and 2V2, only for dilutions. So I have 80 mils here. We don't know the molarity. And we have potassium hydroxide, 126 mils, 0.218 molarity. Okay? So again, we do the same thing. We take moles of this guy and then convert mole-to-mole ratio. Get the moles here, divide by 80 divided by 1,000. You should be able to get the molarity there. So I'm going to work it out real quickly here. 126 mils of KOH. Liter, 1,000 milliliters. And then we'll do the molarity. And then we'll do the mole-to-mole ratio. Then you have moles of H3PO4. Okay? This one here will keep 3 suffix. You end up getting 9.16 times 10 to the minus 3 moles of H3PO4. Now once you get that here, you take that because you need that for molarity. You take the moles from 9.16 times 10 to the minus 3 moles of H3PO4 divided by the volume in 80 mils per and in liters is 0.0800 liter. Okay, so our molarity in this case is 0.114. If you forgot the 1:3 ratio, you would have gotten the wrong answer. So really important to make sure your equations are balanced. Okay? All right, so that's all about molarity stuff. We want to talk about electrolytes, solutions or electrolytes. So sometimes when you pour stuff in like a solution phase here, okay, then you go ahead and stick them in some, stick a electrical circuit, like some electrodes, and then you have it hooked up to a light bulb. Certain solutions will light up the light bulb, and some won't. The ones that light up the light bulb are electrolyte solution because they have ions and electrons floating in there. So whenever you see there's presence of ions in your solution, that will make sure it's an electrolyte and it will turn on the light bulb. If you don't have ions in the solution, like for example for sugar, it won't turn on the light bulb. It won't light it up. So this one here is a non-electrolyte. This one here, the salt, is an electrolyte solution. Okay? So you see non-electrolyte, it dissolves in water but does not produce ions. So anything that's a molecule remains intact, like sugar molecule, that won't break apart into ions because sugar is C6H12O6, right? And then you have table salt, NaCl. Well, that's going to turn into Na plus and Cl minus. That's why this one lights, the light bulb comes on. So you got to remember, ionic compounds will dissolve, so they are electrolytes. Molecular compounds do not dissolve, so they're most of the time non-electrolytes. Now there are some exceptions. Okay, I want to show you the cool exceptions that has to do with acids. So for acids, we have strong acids and weak acids. So there are some acids that are completely ionized, 100%, and then there's some are weak acids. Weak acids can ionize, but it's not 100%. It ionizes to H plus and acetate ion, and it's like, hey, you know what? Let me go ahead and go back and make a molecule again. So it kind of goes back and forth. And because it goes back and forth like that, it's kind of halfway electrolyte, halfway non-electrolyte. So we call these guys the weak electrolytes. This one here is a strong electrolyte because it's completely dissociates. Okay? So over here it says strong electrolytes are everything that completely dissolves 100%. So ionic compounds and strong acids, okay? Weak electrolytes are stuff that kind of go back and forth. So weak acids are the examples. So a cool example of weak acid is vinegar. So if you were to take a solution of hydrochloric acid, you stuck something like your system in there, the light bulbs will turn on and be bright. If you stuck it in vinegar, which is acetic acid, the light bulb will kind of just be a little dim. If you put it in a sugar water, it is not going to light up at all. Okay, so that's how you can tell electrolytes versus non-electrolytes. And then among the electrolytes, you have strong electrolytes and weak electrolytes. So they kind of show you a picture right there. See how that's vinegar right here? That's really dim. Sugar, you don't see any light. And then for table salt, the light bulb goes on bright. Okay? All right, so there are cases where ionic compounds can be soluble in water and some are not soluble in water. The ones that are soluble in water, they can stay as ion forms like this. Silver nitrate stays in ion forms. But whenever you have, if you pour sources of silver ion and chloride ion in here, what happens is silver and chloride like, oh wait, let's go ahead and join forces and we'll precipitate out as a piece of solid right here. Okay, so how can you tell who's going to be soluble or not? We actually have a table of some rules that you have to memorize so you can tell who's going to dissolve and who won't dissolve. Okay, so when something dissolves, it breaks apart into ions. Okay, just make sure you know that. Now, polyatomic ions, they kind of stay as one unit here. So basically break into cation and anions, okay? Cation, anion, cation, anion, right there. So that's how you dissociate, and then you make ions. When you make ions like that, it will be an electrolyte. So let's talk about how we can tell who's going to be soluble and who's not. So this is slide number 33. I want you guys to go ahead and memorize this, make flashcards. Now, if you have lithium ion, sodium ion, potassium ion, and ammonium ion in your compound, they will always, always, always be soluble, no matter who they're paired with. So who are these cations paired with? Remember, cations are going to pair with anions, okay? So plus minus charge are attracted to each other to make a compound. So if you have any of these cations in there, your solution will always be soluble, and there will not be any solids forming. There will not be any precipitation happening. All nitrates and all acetates are also always, always soluble. No matter what cation is paired with these guys here, they will always be soluble. And then chloride, bromide, and iodide, most of the time they're soluble unless they are paired with silver, mercury, or lead, okay? And then sulfates are mostly soluble unless they're paired with strontium, barium, lead, silver, or calcium. So you just want to memorize who's soluble and some exceptions right there. Okay? Now, generally insoluble, all hydroxides and sulfides are insoluble unless paired with these guys. Well, these, yeah, because these are the ones that are always soluble. Okay? Lithium, sodium, potassium, and ammonium. And then when S2 pairs with calcium, strontium, and barium, it's going to be soluble. So these are the exceptions. When hydroxide pairs with calcium, strontium, and barium, they're also slightly soluble. So that's the exception right there. The carbonate and phosphate generally are insoluble unless paired with lithium, sodium, potassium, or ammonium. Okay? So, and then it tells you predict whether each compound is soluble and insoluble. So you basically just take a look here. So the first one is PbCl2, and you take a look up here. Cl and PbCl2 generally are mostly soluble unless paired with Pb. So PbCl2 is one of the exceptions where PbCl2 will be, this one here will be insoluble. Okay, so insoluble, it will create a solid, precipitation will happen. And then the next one is CuCl2. You look at Cl here, is Cu on the exception list? Nope. So CuCl2 will be soluble. It will be completely staying in an ionic form as aqueous form. And then calcium nitrate. So nitrates on a list where it's always soluble with no exceptions. So that's also soluble. Okay. Now barium sulfate. So sulfate was on a list that's mostly soluble unless paired with barium. So this one here is an exception. This is insoluble and will create a solid. So how you make these solutions form or solid or not is basically you have this part of the chapter is called reactions of aqueous solutions. Okay, so you have to have aqueous solutions reacting with each other, and sometimes you pour the right combination, you can make precipitation. So it says here, the first one, it says precipitation reactions are when a solid forms after you mix two aqueous solutions together. How can you tell when they'll form? Well, it depends on the chart of solubility here. So in this case here, they're going to pour some Ki aqueous solution into some lead-2 nitrate solution. And as soon as you pour it in, you see the yellow solid start forming because PbI2 is being formed. So I want to go ahead and talk to you about this equation here and how we can write something called complete ionic equation, net ionic equation, and how we can tell who's going to be precipitating or not. I'm just going to use a cute little, funny little weird analogy story so it'll help us remember things a little bit better. Okay, so I am going to refer to stuff with just just, using our story here. So let's go ahead and start. So now I have a scenario where I have Ki aqueous. So what's the name of this guy? This is potassium iodide, okay? Plus PbNO3 2 aqueous. So this one is called lead 2 nitrate because lead is one of those that changes its name. So lead 2 nitrate. So here's our story. These are all aqueous solutions. So they're in the dating pool. Okay, we call it pool because we're in aqueous pool here. So it's all in water. So we call this a dating pool. So when you're in a dating pool and you're in aqueous form, really what you're existing as is this. K aqueous, I aqueous, Pb aqueous. So of course you gotta know the charges over here. And then I'll write the nitrate just once. Okay, so we have Mr. Potassium, Mr. Lead, Miss Iodide, and Miss Nitrate. They're all in a dating pool because they're aqueous. Aqueous is in a dating pool. And they were previously dating, K and I were dating, PbNO3 were dating, okay? So, and then I guess, K is pretty picky. I maybe talks too much and K just wants to be quiet all the time. So they're not very compatible. And then we have Mr. Lead here, Pb2 plus. He likes to play video games and she doesn't like to play video games. So that's not gonna work. So they're gonna break up now. So they're all in a dating pool here, okay? So when they're in a dating pool, and let's say they go to a dating event, like a mixture thing, I don't know if you guys still do that. You just see on the TV, the movies all the time, right? So anyway, so they go to this mixer event, and then what do they do? Mr. Potassium is over there. He's like, if I see Miss Iodide there, I am not going to talk to her. I'm going to turn and walk the other direction. Okay? So that means you don't date your ex. Just remember that. These guys were previously dating together, and you don't want to date your ex again. There's a reason why you broke up with him. Okay? So what's going to happen is Mr. Potassium is going to walk around, sees Miss Ida on the corner room. He's like, okay, walk the other direction. So he walks the other direction. Okay? And he's gonna look and see, oh, look, there's Miss Nitrate in her red dress. She looks so pretty, let's go talk to her. So what's gonna happen is instead of going with the ex, he's gonna go with a new partner. Now remember, you have to make sure the opposite charges are there, okay? So you gotta remember your charges. You gotta be plus and minus to make one pair, and another positive and another negative to make a different pair. So in this case here, Mr. Potassium is going to ask Miss Nitrate out, or maybe they'll just go and talk together, okay? They're gonna talk. See how things work, okay? So that's the potential couple right there. You don't date your ex, so you date the other person. That one right there, okay? And then Miss Iodide is like, well, I see Mr. Potassium over there talking to Miss Nitrate, never mind. I'm gonna go ahead and talk to Mr. Lead. So then we have Iodide is going to talk to Lead. So here's my other potential couple. So these are my potential couples now. Okay, so sometimes you date, people just, want to keep dating. They're serial daters. Those are the ones that will always stay in a dating pool. Okay, they're always going to stay in a dating pool because they just want to date. They don't want to commit. They want to get married. But sometimes you just meet the right person, and when you meet the right person, you'll know it. You want to go ahead and leave the dating pool and get married and live happily ever after. Okay? So who in the world is going to leave the dating pool, and who in the world is going to stay dating forever in a dating pool? So we have to confer with the book of love. So what was the book of love again? So this is our book of love right here that you want to memorize, okay? So the book of love says, this is like I guess the matchmaker's zodiac book or something, where they look up, okay, so you guys are compatible this and this way, blah, blah, blah. And then it turns out that potassium and nitrate are always soluble. Potassium, always soluble. Nitrate, always soluble. These guys here are your serial daters. Always, always soluble. Never, never precipitate or leave the dating pool, okay? And then we have iodide, When iodide meets lead, they're going to live happily ever after. They will precipitate and leave the dating pool. Okay, so that's how you know. So this is what they call the double displacement. They say all you do is crisscross like that. But then when you talk about it like that, they're like, well, that doesn't make sense. People don't get the arrows and they get all mixed up. So when we break them apart and say you don't date your ex and you make sure you get the opposite charges, it's a little easier to remember. Okay, so we have these two couples here. This one's the serial dater. This one's going to go ahead and get married. So I want to go ahead and write the complete picture of their dating story and then how they got married. And then we'll write the highlight of the wedding. Okay, so the first one we call is called the complete ionic equation. Complete ionic equation is basically the entire story of their dating story, including their exes and stuff. So I'm going to go ahead and write. At first, there was Mr. Potassium. And then in the dating pool, there was Miss Iodide in the dating pool. And then there was Mr. Lead in the dating pool. Everybody was aqueous. Everybody was in the dating pool. And there's Miss Nitrate in the dating pool. Okay? So these are all in the dating pool. And then, you know, potassium decides to date nitrate. Lead decides to date iodide, or, you know, well, whoever can decide. The girl can decide to date the boy too, whichever way. Just so they're going to pair up, but they won't date their ex. Okay? So when you pair them together, you have two potential couples. Now, these guys are always going to be serial daters. So they're going to stay serial daters, so they stay the same. Because they don't leave the dating pool. Only the couple that leaves dating pool is written together as one solid unit. Haha, get it? I said solid. Okay, so the solid unit is PbI2 solid. So this is a solid relationship. They just precipitated out of the relationship. Okay? Now, so that's the entire story. Now, when you are at the wedding, nobody wants to hear about which exes you dated. So the net ionic equation will only tell you the story where at first there was Miss Iodide and then there was Mr. Lead. Both in the dating pool, they met each other. They decided to leave the dating pool and create a solid relationship. Okay, so you notice all you do here, the difference between up here and down here is you remove the spectator ions. So who are my spectator ions? It's this guy, this one, and this one. See how they stay the same? All these ones here, they're called spectator ions. When you remove the spectator ions from the complete ionic equation, you will get the net ionic equation. Now remember, the couple that is solid after we refer to the book of love will be written as one unit together as a compound that's solid because it precipitates and leaves the dating pool. Okay, so that's how you will write complete ionic equation, that ionic equation. And then remember this guy here, because it's insoluble, according to the list of Book of Love here, it will result in precipitation. Okay, so it will precipitate out of the solution. Something that is soluble will stay aqueous forever and will not leave the solution. Okay, so that's what our examples were. So let's try one more. So we did PbCl2, CuCl2. We did these guys here, right? CuCl2, calcium nitrate, and then we have barium sulfate. What about another example? Maybe we want to look at aluminum hydroxide. Okay, so if you have aluminum hydroxide, how can you decide if aluminum hydroxide will be soluble or not? So you say all hydroxides are generally insoluble unless paired with Li and NaK ammonium or calcium, strontium, barium. So aluminum is not on that list here. So aluminum hydroxide, AlOH3, will be insoluble, and it will precipitate out of your solution right there. Okay, so let's, and then sometimes you get a combination like this, where you have Ki and NaCl. So, and your potential options are Ki, K and Cl, and Na and I. Well, Na is always soluble no matter who you pair it with. K is always soluble no matter who you pair it with. These are the serial daters. So it didn't even matter who the behind things were. They will always be aqueous solutions. So there will be a no reaction here. There's no possible combination that will give you any solids. So when you have things that combine has no solid, just write no reaction, okay? And then for example here, this one here, you have two options. You ended up with one solid and one aqueous. Now sometimes we can get crazy and we can get two solids out of our equations here. So here's another option right here. In this question here, they say you have K2, CO3, and NiCl2. Remember, we don't date our x's, so we go the opposite direction, okay? So our possible products are NiCO3 and KCl. So I know KCl is going to be the serial data because all K is always the serial data, right? That's one of my exceptions, okay? But then let's look at the carbonate here. It's nickel and carbonate on there. So on our precipitation rules here, it says carbonates are generally insoluble unless paired with the Li, NaK, or NH4. So basically nickel and carbonate here are going to be insoluble, okay? So that means it will create a precipitation. So let's go ahead and show you. We would have to write this one as a solid unit that precipitates out of our solution, okay? So let's practice writing some of these out on that ionic equation anyway. So and then here's one. See our possible products here? Both of them are aqueous. So this one here has no reaction. So that's why you write no reaction right there. All right. Let's practice. Let's go ahead and practice this question here. I'll go ahead and write it up for you guys. And there's more on your slides too. You guys can practice later, but I'm gonna go ahead and write one out, okay? So let's go with the question. We have 3SrCl2. And you're like, do I know the name of this? You gotta remember the names of these guys. This is strontium. And then strontium is in group 2. So you don't need the Roman numeral. Strontium chloride, okay? And then you add this with Li3PO4. So what's the name of Li3PO4 here? It's going to be lithium phosphate. I guess I should have made you balance it, really. And then LiCl, lithium chloride, and then strontium phosphate. Okay, so we can start balancing. So I had a 3 here because there was a 3 here. And in my Cl, I have 6 of them. So I know I have to put a 6 here. And then because of that, that's why I know this one is also 6. So you can balance it like that, okay? But anyway, we have our options here. So potential options are, we gotta write the complete ionic equation. And we gotta write the net ionic equation. Whoa, is it like shaking the whole time? Fix that. All right, so now we have that. Let's go ahead and write them out, okay? So remember, we only write this solid in the end, everybody else is in aqueous form. So at first they were in a dating pool. You have 3SR2 plus, and then I have 6Cl, because you have to start thinking how many 3 times 2 is 6 here, and then 3 is right there, okay? And that's also aqueous, so strontium and chloride will in a dating pool. You also have lithium in a dating pool, and you also have phosphate in a dating pool. Okay, and then you make a couple that's always the serial dater, so we'll write them as still dating in the dating pool. Okay, and then we write this couple that precipitate out as one unit. SR3, PO4, 2 solid. And that is my complete ionic equation. You have to write at first, they were all in a dating pool, all aqueous. And then these couples stayed aqueous because they're serial daters. And then that one here precipitates. Only one couple precipitates out here. So if you remove Cl and Li from your net ionic equation, because those are the spectator ions, you will get the net ionic equation. So the net ionic equation is 3Sr2 plus aqueous, strontium, met, phosphate, and they lived happily ever after. Precipitate out. So it's SR3, PO4, 2 solid. And that's how you will write it. Okay, so I want to talk about the next type of equation. So this is the first one, reactions of aqueous solution. The first set is going to be precipitation reaction. So precipitation, because you have a solid that precipitates out, okay? Now, let's talk about some other kinds of equation or reactions. So another one here is, so the first one is precipitation, the second one is acid-base, the third one is gas evolution, okay? So let's look at acid-base reaction. Acid-base reaction are also neutralizations because you have an acid and a base. We have H plus and OH minus in there, and you will always make water. The net ion equation for acid-base equation is always H plus and OH minus makes water. Okay, so when you see this, you know there's an acid-base reaction happening. All right, so let's talk about acids. Acids are defined as something when you put in water, it will create H plus. Sometimes they call it H3O plus. They use it interchangeably. But basically the definition of acid is when you put acid in water, it forms H plus ions, okay? And then when you put base in water, the definition is when you put base in water, you make hydroxide ions. So one is the source of H plus, one is the source of hydroxide ions, and that's why we can make water from it, okay? And sometimes they say here, look at this example here. We have sulfuric acid that has 2 H plus coming off, and then strontium hydroxide has two hydroxides coming out of it. So sometimes it gives out more than one H and OH. In that case, you would just make more water molecules, okay? But the simplified version of all the net ion equation is H plus OH minus equals to H2O. So I wanted to show an example of acid-base titration here. We have this on the slides here. Here's a very simple one. Hydrochloric acid and sodium hydroxide can be combined to make water and table salt. Okay, so we can write an equation for this. This will be simple to write. So let's go ahead and try that. We'll try another example as well. And I'll teach you also how to write the net ionic equation and the complete ionic equation for it. So let's go ahead and start with this one first. So HCl plus NaOH equals goes to H2O and NaCl. Okay, so that's the first one. Now, when we want to write the complete ionic equation, complete ionic equation. It will be H plus Cl minus, all in aqueous form, plus sodium in aqueous form, plus hydroxide in aqueous form. Okay, now we don't have a solid here that's formed, but what do we form? In acid base, we form water. So we write water as a unit that's separate from the aqueous. Okay, now we have Na plus still at aqueous, and then Cl as aqueous still. That's how you write an ionic equation. I mean, not net, complete ionic equation for acid base. Okay, so this is acid base. This one up here was precipitation. So let me write it out. Okay, that's the second category here. Now, when you do the net ionic equation, you literally remove the NaCl. Because those are your spectator ion, they didn't change. So it's H plus OH minus goes to H2O here. Okay, so let's try one more acid base. This time, I'm going to give you the names and you figure out the formula. So what we're going to do is we are going to work on hydroiodic acid, and we're going to pair it with barium hydroxide. Okay, so take a moment and try to see if you remember how to write these rules here. Hydroiodic acid. So hydroiodic acid over here is basically a binary acid. It's hydroic acid, remember? So this one is going to be HI. And then barium hydroxide is BaOH2. So you need to know that part. And then when you do that, you have mix and match here. I will go with the barium and then that one. And now you can see how it's not balanced. So I'm going to go ahead and help you write that out. So you will make water and you will make BaI2. So on your BaI2, I want you guys to, so I'll show you your book of love. So you see I here? Is it paired with Ba as an exception? Nope. So BaI2 will be aqueous. Okay. Sometimes you see a solid and water coming out. So that would be kind of cool if you acid base and precipitation at the same time. But this one is not. This is just acid base. Okay. And then we also got to balance it out because we have 2 iodine here. I'll put 2. And then I know I have 2 water because there's 2 hydroxide and 2 H plus. And that should balance everything out. Now that we know everything from the molecular equation here, and it's all balanced, we can go ahead and write the complete ionic equation. And the net ionic equation. Okay, so this one here is 2H plus aqueous plus 2I minus aqueous plus Ba2 plus aqueous plus 2OH aqueous equals to 2H2O liquid plus Ba, oh, I forgot to, Ba2 plus aqueous, and then 2I aqueous. Okay, just enough space. And then remove the spectator ion, Ba and I. What do we get? We get 2H plus aqueous plus 2 OH. Oh, a little too excited there. 2 OH aqueous makes 2 water. Okay, then that's liquid phase. Now, because it's 2 and 2 and 2, a lot of times they just simplify and write this. H plus OH minus equals to H2O. Same thing, it's still correct. Okay, so that's how we would write it for an acid base. So we have a lot more examples on the slides. Feel free to go on your slides and practice some more of these guys. So I wanted to show you the other examples that they had. There's these guys here. And then there are some that were like gases. These guys here. See this one here, this example here on slide 50 is acid base and precipitation at the same time. So that one's pretty cool. Okay, so you can practice them. The answers are on the slides itself. So let's keep going. While we're talking about acid base here, let's go ahead and show you the stuff that goes in the lab when we do acid base titration. So what are titrations? Basically, you use it to figure out concentrations of solutions. Like one of them will be an unknown, one of them will be known. And then you use something called burette. Now, burette here is really weird compared to a graduated cylinder, because graduated cylinders, the marking is like from the bottom going up, the bottom is small and you fill it up, it gets higher. But burette is upside down because you hang it on the top, and your numbers is basically backwards, because your graduated cylinder, you're used to seeing the 0 on the bottom and then the bigger numbers on the top. The burette actually does it backwards because the 0 will be on the top, and as you drop them down, the number gets bigger. The more of the volume that you release into the flask, the number gets bigger. So the number is essentially reading backwards. So a lot of students, when you read the burette, I want you to read it really, really carefully. Do not read it upside down. That happens so often. And that's a really common mistake. We don't want that to happen. So we will be practicing how to read burettes in the lab and also in the lecture. I'll have some pictures up here. So we will be using a burette. Now, when you end your experiment is when you see a color change. When you see a color change, it's because you put an indicator that will change colors at the end point. Okay? It changes color at the end point, and the end point is found at the color change where it's an equivalence point of moles of H equals to moles of OH here. Okay, so basically titration is you add either acid to base or base to acid until the H and OH are equal amounts at the equivalence point. And we put an indicator, a chemical that changes color when the equivalence point hits, and we see the color visually change, and we call that visual change here the endpoint. Okay, so endpoint and equivalence point is kind of the same thing. It's just this one is because the presence of the indicator that changes color. Equivalence point is really the definition of H and OH being equal. All right, so let's take a look at how we want to read burettes. So, well, should I cover the answer? Okay, let's pretend you don't see those answers right there. I'm going to cover it up. Too late now, you already saw the answers. But we can still try, okay? So I'm going to zoom in. Now, notice it's upside down. So if you were in a graduate cylinder, remember number in a graduate cylinder is 0, and then you fill it up, you go up higher, and the number gets bigger. But look at this. The number is getting smaller as you go up higher. That's the opposite of a graduated cylinder, okay? So it's different here, but to read it, whenever you get confused, just read. Okay, I have to read the lower meniscus, which is that line on the bottom right there. And I have to read that line, and this is 40, that's 41, that's 42. And you're like, okay, well, so it's higher than 41, but less than 42. So it should be 41 point something. Okay, so you always read what are the numbers in between, what should my number be in between. So let's go a step further. We know it's higher than 41. So now you start looking at these lines here. That's 41, that's 41.1, that's 41.2. It's actually in between 41.1 and 41.2. Agree? So because you can read 41.1, 41.2, you have to estimate one more decimal place. I think it looks kind of smack in the middle. Actually, it might be pretty close to the 41.2. So an estimate number would be like maybe like this one here, 41.15. Now, if you were looking, this is where the number on the second decimal place varies a little bit because of reading. You know, it's subjective between person to person. And when you read a burette, make sure you are eye level. Anytime you read any volume, make sure your eye is at the same level as the lower meniscus. Okay? So you can estimate this to be 41.15. Someone else might say it's 41.17 or 41.18. Doesn't matter as long as it's in that range. Okay? Between 41.1 and 41.2. How do I know that? Because you see here, this is 41, 41.1, 41.2. 3, 4, 5. That's 41 and a half, 0.6, 0.7, 0.8, 0.9, 42.0. Okay, so you gotta just read it like that. So let's take a look at this other one here. Since you already saw the answers, pretend you didn't. Now take a look here. This is 23, 24, and 25. And I have to read the lower meniscus. So this is 24.1, 24.2. I guess, you know, I know the answer says it's 24.20. If you really looked at it, it kind of almost could be 24.19, right? So that's really subjective, but that's where you start to estimate that last decimal place. 24.19 versus 24.20 isn't that far off. Okay, so hopefully everyone is comfortable reading a burette. You will need to practice this when you are in lab. If you're not in lab, still need to practice because you're going to see these kind of readings show up on your lab quizzes and exams, okay? All right. So let's take a look here with this titration. This is something you will do in lab. You will be putting some base, so it has hydroxide, into some acid, maybe usually it's hydrochloric acid and then base. So sometimes you put the acid in there and base on the bottom. It really depends on the experiment. Okay, so in this case here, the titrant is the base solution in the burette. So the burette is what holds the titrant. And then titrant is added to the flask. As you add the OH in, it starts to change the chemistry down here. So H is starting to meet with OH and starting to make water. At some point where you have H and OH equal amounts, this solution will turn pink. This indicator that we're using is called phenolphthalein. Okay, you will be using this in lab and it will change color to a faint pink. The lighter pink, the better it is, the more accurate it will be. If you go darker pink, you're kind of like, that's kind of danger zone. And when you're hot pink, you're way too far out. Okay, so you want to be patient as you get closer, as you drip it down, the pink, and you want to shake this flask, like hold it and mix it around. And when you're mixing it, the pink disappears every time it drops in. It turns a little bit pink, it disappears. And then the pink stays longer and longer. Eventually the pink just stays constant, but it's really light pink. That's when you want to stop. Okay, so this is a skill that you will be practicing in that. It's kind of a fun experiment. Once you get the technique down, it's really easy. But to learn the technique, it takes a lot of practice and patience. So make sure you guys have fun practicing doing this. Okay, so that is titration. I'll show you more colors right there. You went a little too far here. This is how when you pink, it's kind of a swirl. And if you shake it around and it disappears, you're not quite there. And then at some point, the one drop or maybe even half a drop, you put that in, you swirl, the whole thing turns light pink. It's really cool. All right, so let's do some calculation now that has to do with titrations, okay? So let's see. I will write the question out for you. Mil, 10.00 mil sample of HCl solution of unknown concentration requires 12.54 milliliters of a 0.100 molarity NaOH solution to reach the equivalence point. Okay, what is the molarity of HCl? So it doesn't sound like what we've been doing this whole time, but this time you need to write your own equation, right? Because it's HCl plus NaOH, you make water and NaCl. Lucky for you is 1 to 1 to 1 to 1. It's already balanced. You have to write it out because a lot of times these acid bases are not 1 to 1, and that's when your mole to mole ratio are off. Okay, so you gotta be really careful. Always write the equation out and make sure it's balanced before you do your calculations. So it says that you have 10 mils of this guy. You don't know the molarity. And then sodium hydroxide, you have 12.54 mils. You know it's 0.1 molarity. So we're gonna go ahead and calculate that, okay? So same thing, we start over here, 12.54 mils of NaOH. Gotta convert it to liters first. One liter is 1,000 milliliter. Okay, I'm gonna change pens because it keeps running out. Hopefully this one works better. And then my molarity is 0.100 moles per 1 liter. This one is much better. And then the mole to mole ratio, lucky for us, is 1 to 1. 1 mole of NaOH is to 1 mole of HCl. So you want to make sure you always write the equation out and balance it. Sometimes, a lot of times, it won't be 1 to 1, okay? So let's get our moles here because they gave us the volume, and you take the moles divided by the volume in liters, we will get molarity. So the moles here is, you want to keep 3 sig figs here. This is 4, that's 3, we keep 3, so 1.25 times 10 to the minus 3 moles HCl, and then the molarity is just take that number, divide by 10 mil, so it's 10 divided by 1,000, 0.01000 liters, and the molarity moles is 1.25 times 10 to the minus 3 moles of HCl. I will get 0.125 molarity of HCl. Okay, so start getting used to these units. Capital M is molarity and mol is mole. We say that 1,000 times, but I just want to make sure you guys are aware and don't make the same mistakes in writing the wrong units. When you write the wrong units for your lab, it's considered wrong work. So you want to make sure you get your units right, okay? So we had 2 kinds of reactions already of aqueous solutions. We had precipitation, we have acid base, we learned to write that ionic equation, complete ionic equation. Now we want to talk about gas evolutions. So for gas evolution, there's all different kinds. So I'll show you a table of it, so we'll take a look. In this case here, if you have metal HS or metal with S, you will form H2S gas. If you have any sort of carbonate or bicarbonate, you will form carbon dioxide gas. Okay? If you have sulfide or bisulfide or hydrogen sulfide, you will get SO2 gas. And then you have ammonium here, you will have ammonia gas. So here are some examples. I don't need you to know exactly how to do these because there's so many different variables. Just know that, you know, every time you see an equation, if you have aqueous and aqueous and aqueous, and then you have gas, that is a gas evolution reaction. Now, sometimes the test questions will ask, which one of these are gas evolution reactions? Then you can find them. But other than that, you don't have to worry about too much about memorizing how the equations come up, but it's pretty cool. You can see like carbon dioxide comes from anything that has carbonate or bicarbonate. Sulfur dioxide comes from sulfide, and then you have hydrogen sulfide comes from anything with sulfide in here, or sulfide. So it's kind of cool, okay? So just make sure you know how to recognize when it's a gas evolution reaction. Now, the next category. So gas evolution reaction actually looks like this. When you put it in, it bubbles. Crazy bubbles comes out. So this bubble here is because we have hydrogen carbonate, bicarbonate, sodium bicarbonate here. That's baking soda. Just pour some baking soda, and this one here is HCl, but you can use vinegar. You can get the same thing. That's the basis of your volcano experiment. Remember your volcano experiments when you were little and you had to do it for your science fair or class? You put like vinegar and baking soda together. That's an acid-base reaction that creates carbon dioxide gas. Kind of cool. It's gas evolution and acid-base reaction at the same time. Okay? So there's that one. Hopefully you can see, but this is on slide number 59 if you want to take a closer look. All right. So the next part here is the last part, last kind of stuff that I want to talk about, but it's pretty important for us to learn. So I want you guys to pay attention. And if you need to take a break, go ahead and take a break now, come back to it, pause this, and come back to this part. This is the last part of chapter 5, but it's really important that you learn this because this comes back again in Chem 2, okay? So we want to talk about oxidation, reduction, reaction. So oxidation reduction, that's such a mouthful. For short, we call it redox, okay? Redox. So it has to do with when you transfer electrons, but sometimes it's not so obvious when you're seeing electrons being transferred, but there is electrons being transferred. So a lot of times you can't quite tell it. So we will be looking at this from another perspective by assigning its oxidation states. Oxidation states are kind of like ion charges, but a little different. So it's just another way we can describe the state of the element, okay? So in this case here, it says, when you talk about losing electrons and gaining electron, oxidation is the process where you lose electrons. Reduction is the process where you gain electrons. That's only if you're talking electrons, if you can see the electrons. And if you have a hard time visualizing electrons, then don't worry about this because I'll teach you another way to determine who's being oxidized and reduced, okay? So the best way to do this is, for example, in this case here, H2 and Cl2 makes HCl, but you can't quite tell who's being, I mean, it's kind of hard to see. You can't see the electrons there, correct? But in this case, if you could tell electrons who was being gained or lost, hydrogen was being oxidized because it lost electrons, chlorine was being reduced because it gained electrons. But you kind of can't tell unless you knew the structures here. See how chlorine was kind of has a bigger electron density here. Hydrogen has a smaller amount, is partially transferred. It's not really obvious, is it? So there's a better way to do this. The better way to do this is to learn to assign oxidation states to all these guys, okay? So assign oxidation states, that's the focus of this part of our chapter. We just have to learn how to do the oxidation states. Based on that, I can teach you how to define who is being oxidized and who is being reduced, okay? So what is an oxidation state? It says here, even though they look like charges, oxidation states are not ion charges. It's very similar, but it's not ion charges. Oxidation states are imaginary charges assigned based on a set of rules. Ion charges are real charges, real measurable charge. Oxidation states are kind of imaginary because you needed to be able to think about something like this, right? That's kind of like, how in the world are you going to measure that charge? So that's why we use oxidation state. So we have priority rules here, okay? So the first rule we want to talk about is all free elements. Now, who in the world are elements? Remember, only from one box of the periodic table, only one type of element, okay? All free elements, that means it's standing by itself, it's not with anybody, and it's neutral. All freestanding elements have an oxidation state of 0. That's by definition. So if you see sodium by itself, chlorine by itself, even though it's diatomic, it's still an element, go ahead and assign 0 for it. Monoatomic ions have an oxidation state equal to the charge of the ions. So Na plus ion is +1, Cl minus is -1 charge. Oxidation state and charge. Oxidation state +1, charge +1, okay? And then it says here, if you have a compound, the sum of all the states of your elements in the compound need to add up to 0 because the compound is neutral. So basically, if you have an ion, polyatomic ion, the sum of all the individual parts in there needs to add up to the charge of the ion. So if you see here, NO3 negative is -1 charge for nitrate, and you see the number for nitrogen and oxygen has to add up to the same as the charge of nitrate. Okay, so basically here are the rules. Number 1, freestanding elements are 0. Ions have the same oxidation state as the charge. When you have a neutral compound, the individual parts of it add up to 0. When you have something with ion, like polyatomic ion, individual parts add to the charge of the polyatomic ion. Okay, and next rule is group 1 metals always have +1. If you don't see group 1 in there, look for group 2 metals. Group 2 will always be assigned as +2. And then the next rule is if you don't see group 1 or group 2, you look for fluorine. Look for fluorine here. Fluorine will be assigned as -1. If you don't see fluorine, look for the next in line. It's hydrogen, is +1. If you don't see hydrogen, go to the next one as oxygen, assigned as -2. And then if you don't see oxygen by itself, anything in group 7 in general is -1. After group 7, you can't find it, look for group 6, -2. You can't find group 6, group 5 is -3. Anybody else not on this list will be calculated, or the leftover will always be calculated. So enough on the rules. I just told you the rules, but we want to go ahead and practice. Okay, so we got to try to practice. So we'll have a lot of different examples here, but once you practice this, I want you to work this out with me, okay? So based on the rules, we can take a look at the rules together, or just slowly do this together with me and then try to do it again without help. See if you remember. First one, Cl2. What's the oxidation state of Cl and Cl2? There's 2 Cl's in there, both of them are same. Each Cl is going to be 0. Why is it 0? Because it is a freestanding element by itself. So oxidation state. All right, so let's do the next one. The next one is Na positive. What's the oxidation state for Na and Na positive? Remember the rule that says, I'll show you the rule. That was a free element, oxidation state 0, monatomic ions, oxidation state equal to the charge. So that one is going to be +1, okay? Now we have K and F. If your K and F is a neutral compound, right? So K and F has to add up to 0. And then K and F, so I'll go ahead and write K and F has to add up to 0 because it's neutral. And then we start looking into my list. The first thing you look for is, can you find group 1? If it's group 1, it's +1. And K, potassium, is in group 1. Okay? So potassium is assigned as +1. And therefore, if I know potassium is +1, I know fluoride has to be -1. Plus, we know the charges, this is K +1, F -1. So we know F is -1 here. Okay? So that's how you assign that. Now, the next one we want to do is CO2. That one doesn't, you can't really see the charges. That's a little harder, right? So this is when it comes in handy. So we have CO2 at 1 carbon and 2 oxygen equals to 0 because it's neutral. Then I have to decide who's my first priority. So my first priority over here was group 1, right? And then I have to calculate what F is. But in this case, what's my first priority? So let's take a look at the priority list. Do you see, whoa, sorry. Do you see group 1? Nope, I see carbon and oxygen. Do you see group 2? Nope, I don't see group 2. So what's the next on the list here? It was, do you see F? Nope, I don't see F. Do you see H? Nope, I don't see H. Do Do you see O? Yes, O. Okay, so O is right here. O is my first priority. Go ahead and assign that as -2. Let's seal that in first, okay? Once you know what O is, you can calculate the leftover, which is C. So C plus 2 of -2 equals to 0. Carbon will therefore be +4. And that's how you know the oxidation state of oxygen and carbon over here for carbon dioxide. Okay? So we're graduating to slightly more complicated cases now. Let's do the next one. SO4 2-. What's the name of this ion? This name is sulfate. Okay? So how in the world I'm going to do this one? So we have to say, well, I know I have sulfur and I have 4 oxygen. They total up to -2. Just based on this formula, it adds up to -2, and 1 sulfur and 4 oxygen. Then I have to go through my list. Do you see group 1? Nope. Do you see group 2? Nope. Do you see F? Nope. Do you see H? Nope. Do you see O? Yes, I see O. So therefore, O is assigned as -2 because that was on our list. Okay, so I'll show you the list again. Right here, you see oxygen assigned as -2. Okay? And then once you decide what oxygen is, you have to calculate what sulfur should be. So let's put it in. Sulfur plus 4 of -2 equals to -2. So what should sulfur be? Sulfur minus 8 is -2. Sulfur is +6. That's how you get the oxidation state of that guy. Okay? So basically, oxidation state is the number oxidation state that every element in every compound has an oxidation state. We have to calculate it. Okay? So let's go to the next one, EF, K2O2. How do we do that one? K2O2. So we have 2K and 2O equals to 0. And then we have to look at our priority list. Who's my priority list? Group 1? Yes, I see group 1. That's group 1 right there. So K is +1. Okay? Once K is +1, we'll plug it in. 2 oxygen equals to -2. Each oxygen is -1. You're like, whoa, if I had assigned oxygen as -2, we would have been in a lot of trouble. And that's why you got to remember your priority rules. Group 1 first, group 2, and then FHO, group 7, 6, and 5. Okay? So in this case, K is +1, O is -1 oxidation state. So EFG, let's do another one, H2O. Let's try that one. What do you think that looks like, H2O? So I have H, 2 H's plus 1 oxygen equals to 0. What's my priority? Group 1, group 2, F, H. H comes first, so H equals to +1. According to my table, I'll show you the list again. Right there, okay? And then H is +1, so we gotta calculate what oxygen is. 2 and +1 plus oxygen equals to 0. O equals to -2. Hopefully we're getting the hang of this, okay? So let's do some more. We want to do another one. Well, let's do hydrogen peroxide this time, H2O2. So what do you think H2O2 is going to be? H2H plus 2 oxygen equals to 0. I'm just going to try to write a number there, 0. Okay, my first priority is hydrogen because it's group 1, group 2, and then FH. Okay, H is +1. And then 2 +1 plus 2 oxygen equals to 0. 2 oxygen is -2. Each oxygen is -1. Okay, so that's how we do that one. So now that we've done all these different ones, I want you to go ahead and apply it to equations. Okay? I want you to apply in equations. We'll do a bunch of equations here. And on every equation, you'll have to do every single one of these elements in every single compound. You have to assign the oxidation state. So let's go ahead and try that. All right, the first one, let me zoom out a little bit. A little bit better. Yeah. Okay. So A is Mg plus 2H2O plus Mg OH2 plus H2. Okay. So this one here, we can go ahead and assign oxidation states for everybody on here. Didn't we just do this just now? Okay, that one we just did a bunch of times. We just did water a bunch of times. Now don't worry about this coefficient here. Just do the molecule. Okay, so Mg is 0, H is 0, right? Remember, because it's freestanding element. So we got to do H2O. Remember H2O, H, 2H plus O is 0. H is plus 1. And then we calculated O as -2. So take your time and do this. You can pause it and then do this, okay? So now we have this guy here. When you see something like this, I like to just break it into ions, so there's less to do. So this is Mg2 plus, and this one is OH negative. Just do it for one of them, okay? So Mg here is plus 2. OH here is O plus H equals to -1. And my priority is H. So O has to be calculated. O is going to be -2. Okay? So I have my numbers now. You see I have magnesium 0, and then hydrogen and magnesium. So now take a look at all these numbers. Do you see an element where the number went up? Where's the number, oxidation number went up? Magnesium went from 0 to 2. Notice that it went from 0 to 2. When it goes up in numbers of oxidation state, this is an oxidation process. Magnesium has been oxidized. Okay? And then if you see anybody that goes down in number, anybody see any number going down? So H is going down from H plus 1 here. This one's plus 1, but this one going to 0. It's from here to there. That one's being reduced, the reduction process. So specifically, hydrogen in water is being reduced. Okay, so that's reduction. Now, when you learn who's being oxidized and who's being reduced, so oxidation is going up in oxidation state, reduction is going down in oxidation state. The guy that's being oxidized is called the reducing agent. The guy that is being reduced is called the oxidizing agent. It's always the opposite process agent. So let me explain why. If oxidation cannot happen without reduction, they're stuck together. Oxidation happens, reduction is there somewhere in there. It's hidden somewhere, maybe you don't see it, but it's there. That's why I call it redox. It always happens hand in hand. If you did not have water, this reaction would not take place. Agree? Magnesium cannot oxidize without water. Therefore, water is the agent for oxidizing, for the oxidation to happen. And that's why the guy that's being reduced is the oxidizing agent. The guy that's being oxidized is the reducing agent, because without magnesium here, water can't just reduce on its own. It needs magnesium to be there. So because magnesium is the reducing agent. Okay, so remember, it's the opposite process. The guy that's undergoing oxidation is the agent for the opposite process, which is reduction. The guy that's being reduced is the agent for the opposite process, which is oxidizing. Okay, so let's keep on moving. Now this B here, you actually do in your lab, in your first experiment of the semester. You put magnesium in hydrochloric acid, and you form MgCl2 and H2 gas. So it's like really cool where the Mg just disappears, the magnesium metal just kind of gets dissolved, and the gases start bubbling out. So it's kind of cool. And it happens really fast, and it feels hot. like the test it gets warm. So it's a fun one to do. It's a magic show. But this one here, we can assign oxidation states too. So let's go ahead and do that. So I like to go ahead and assign the ones that are 0 first. Okay, and then I have H and Cl. H plus Cl equals 0. H is my priority. And then Cl will be calculated as -1. Okay, and then I have Mg and Cl2. So in this case here, Mg, and then you have 2Cl equals 0. Mg is my priority because it's group 2. So Cl plus 2 equals 0. And Mg is 2 right there. And then 2Cl is -2, Cl is -1. Okay, so every time you're in an equation, you can pause it, do all this, and see if it matches with mine. Now that it matches, let's go ahead and determine who's going up and who's going down. Magnesium is going up, agree? So this is being oxidized, oxidation. So this guy is the what agent? The reducing agent, okay? And then who is going down? H is going down. So this is a reduction. So H, specifically H in HCl, that's your oxidizing agent, my guy. Oxidizing agent. Okay. All right. Let's do more. So here's a trick question. I want you to do this one. 2HBr plus CaOH2, 2H2O plus CaBr2H2. So can you tell what kind of equation this is? This is an acid base, okay? Acid base. This is an acid base. I want you to go ahead and do the oxidation states, and then I'll write another one here. 3SrCl2 plus 2I3PO4 Now, I should write it neatly so you can see. And then SR3PO4 plus 6LiCl2. Okay, this one here is what? This is acid base. This one here is precipitation, okay? So if you did all of these guys, oxidation states, you'll be like, what? You'll be really confused because these guys here, acid base, let me write it down. Acid, base, and precipitation. Reactions are not redox. Okay, they're not redox. Because if you did all of these here, you will see that the oxidation states did not change for both sides. Like everybody has the oxidation state stay the same. So I'm gonna go ahead and assign them, and I want you to practice doing it because phosphate will be a good one to do. Although you didn't need to because you see how phosphate doesn't change, that means phosphate stays as phosphate. And when you have like ion exchange double displacement happening, that's when you don't have a redox, okay? That's how you can tell that's not a redox reaction when you're just switching around the ions like that. But I'm gonna go ahead and show you how to calculate these with the answers, and then you can practice because it's good to practice these things. So H here is +1, Br is -1. When you do this, I'll do calcium separately, +2, and then you see how we did this one up here, magnesium? I'm gonna do the same way, okay? So when I split the calcium hydroxide, I can get calcium, and then my oxygen and hydrogen comes next. So I'll be able to assign H is +1, O is -2 here. And then for water, H is +1. You can calculate O is -2. For CaBr2, same thing. Ca is +2. Br can be calculated to be -1. Okay, so you can do that, and you can see CBr is -1, calcium is +2, H is +1, O is -2. Nobody changed. Okay, it's not a redox. Okay, next one here, also not a redox. Why? We can take a look. So strontium and chloride, so Sr is group 2, and then Cl is calculated. -1. So you get fast like this after you've done it 1,000 times, but you need to practice, okay, if you're not familiar with it. So when you do this one, I like to split it apart. Lithium is +1, and then we do phosphate by itself. So I'll show you phosphate because I don't think I've shown you phosphate yet. So let's go ahead and do it. PO4, 3-. Okay, we gotta do 1P plus 4 oxygen equals to -3. And I will assign oxygen first because oxygen is my priority. So oxygen is -2. Okay, and we plug -2 in there. P minus 8 equals to -3. You guys see that? So P equals to +5. Okay, and when you do this phosphate over here, you get the exact same numbers because it's still phosphate. It's strontium and phosphate again. So strontium here is +2, and then PO4 is the same thing. So you get O again is -2. And then P again is +5. You get the same exact answer. And then Li is +1. And then Cl is -1. So nobody changed. That's why it's not a redox. When you have double displacement like that, it's not a redox, okay? Or when you have gases being formed, things like that, these are redox right here. Okay, let's do more. Let's see, we have more to practice. Yeah, we only have a few more. And then that's the end of this chapter, okay? So you guys made it. We're almost there. I do want you to keep practicing because this is very, very important to master this material. If you have to take a break, come back to it. The video will be here. So this one's easier though. So it's zinc solid plus iron 2 plus aqueous ion equals zinc 2 plus aqueous ion and iron solid. So this one you can assign an oxidation state. Zinc is 0, Fe2 plus is +2, zinc 2 plus is 2, +2 also, Fe is solid by itself, so it's 0. So you can tell zinc has gone up, so it's being oxidized. And zinc is called the reducing agent. And then iron is coming down in number as being reduced. So the reduction. And iron 2 plus is the what agent? Oxidizing agent. Specifically iron 2 plus, not iron, but iron 2 plus. Okay, the guy that's being reduced is the agent for oxidizing. All right, let's do another one here. So this one here is methanol combustion. Okay, so methanol is relative of, well, you guys heard of methanol. And methanol is 1 carbon less than ethanol, which is the alcohol that people consume. You know, yeast can make that. Yeast. And then, you know, that's in alcohol. People that drink alcohol. That's ethanol. This is methanol. Okay? So 2 methanol plus oxygen. We burn it up. We can get 2 carbon dioxide plus 4 H2O gas. Now this here is the combustion reaction. When you have something that's carbon, oxygen, hydrogen, and you plus water, I mean not plus water, plus oxygen, you're burning it out and you get carbon dioxide and water. Whenever you add oxygen and you get carbon dioxide and water, this one here is the combustion. Okay, and all combustion are redox. So we got that one. So let's go ahead and assign oxidation states for these guys. This one's 0. I like to do the 0 ones first. That's the only 0 we got. Well, we did carbon dioxide earlier, we did water earlier, so we can go ahead and put that answer down. On carbon dioxide, I noticed my oxygen was my priority, and then my carbon was calculated to be +4. We did that on a previous page. We also did water, so I'll go ahead and write the answer down. H is +1. If you need to, go back and take a look at your previous page. Okay? And then let's do this guy. This guy is different. We haven't done it. So we have carbon plus, how many hydrogens do I have? I have 4 plus 1 oxygen that equals to 0. Okay, now who's my first priority? My first priority is hydrogen. Group 1, group 2, F, H, and then O. Okay, so H is +1. And then I have another priority, O is -2. So I always assign the front ones and then leave the last one for calculation. So I assign H first and then assign O, and then I leave carbon for calculation. So in this case, I have to calculate what carbon. Carbon plus 4, +1, plus -2 equals to 0. Agree? So if you do this, carbon is +2 equals to 0, so carbon equals to -2. Then you can see carbon has now changed from -2 to +4. Carbon has been oxidized. The carbon of methanol has been oxidized, making this guy, the carbon of methanol, the reducing agent. Okay? And let's take a look. Oxygen is 0 here, and it turns to oxygen -2 here. Agree? So this here is reduction. You really close both of them. So this is a reduction process. Oxygen, therefore, is the oxidizing agent. All right, let's do the last one. Ni solid plus 2AgClO4Aq. You need to start remembering what the names of these guys are. You know the name of this guy? Silver doesn't change, so you don't need a Roman numeral. It's silver was this one, perchlorate. Okay? Silver perchlorate. And then you have nickel 2 perchlorate. Plus silver. Okay, so this one is 0. Nickel is 0. Silver is 0. Now we gotta solve these guys. Now, notice that didn't change. If I were you, you're on a test, don't waste your time calculating it because Cl and O there did not change values. Did not change. But I'll go ahead and do one of them, and then you can still see how we can do perchlorate, okay? But what's this guy's unit now? Perchlorate is ClO4 -1, so silver is +1 charge. So that means silver is +1 oxidation state. Okay, so ClO4 negative is what we're going to calculate. And then nickel here is 2+, so it's nickel is +2 here. Okay, I want to go ahead and show you this, although you don't need it. In this question, we are learning how to calculate oxidation states. So Cl plus, not equals, it's plus 4 oxygen equals to -1. Who's my priority? Group 1, group 2, F, H, O. O came first. O equals to -2. Then we plug it in, Cl plus 4 times -2 equals to -1. Cl equals to +7. Okay, and if you do the same thing for the perchlorate here, you get the same answer. So in this case, you still get oxygen as -2, and you get the Cl as +7 again. Okay, But what's changing? The nickel has now been oxidized, and the silver has been reduced. So silver is called what? The oxidizing agent. Okay? Nickel is called what? The reducing agent. Okay? So make sure you guys practice, and this is the end of chapter 5. I'll see you guys for chapter 6.